So welcome back students to one more session of your solid state chapter. We're almost coming to the end of the chapter, right? So till now what did we learn? We have learned the concept or the classification of solids. We have learned how to calculate number of atoms. We have learned how to calculate or find out the density of a solid, right? Then we also studied about Bravais lattices. I also taught you the concept of voids. Then I taught you the packing fraction. What is the packing fraction? What is a type of arrangement? How are they packed? Different varieties in 2-dimensional, 1-dimensional, 3-dimensional. Now I'm coming to the topic. No, I also taught you a topic called radius ratio and its relation with its coordination number. Now today's topic I'm going to teach you about imperfections or defects in solids. Right. So what actually are imperfections, defects? So very well known, solids are tightly packed, right? There is very less space between the atoms because of their arrangement, right? Suppose if there is any deviation, means a small deviation from this perfectly ordered arrangement happens, a small deviation or small gap is observed, or it happens in the solid. So any deviation from the perfectly arranged or perfectly ordered arrangement of solids, okay, arrangement of constituents, not solids. Again, I'm repeating. Let us write if it is confusing you. Imperfections is any deviation from perfectly ordered arrangement of what? Of constituents of a solid. Then it is called imperfection or defects. Done. Now what will happen because of this defects? Because of this defects, it will lead to change in properties of solids, right? So, and they'll also be it will introduce special properties in solids because the alignment or the arrangement is changed, isn't it? Now, so when I have to speak about solid state chapter, defects in solids, what are the different varieties of defects in solids? Let's see. So solid or defects basically are classified into two categories. One is a point defect. The other is a line defect. Point defect and line defect, right? So here point defect means a deviation from ideal arrangement around a point or atom. Suppose, so this is an arrangement of atom, right? So one more series, one cation, anion. I'm all drawing in one size. One smaller cation, bigger anion, bigger anion, like that it will be. Okay, I just made this for an example. Sorry for this, right? So here, any one point, suppose if there is any one point, if there is deviation from this point, then it is called point defect. Means what we have to say, deviation from ideal arrangement around a point or an atom. So basically don't take this, this is basically wrong. I need to draw like this: cation, anion, cation, anion, cation, anion, like this. Again, below the cation it is anion, below the anion it is cation, again like that. So if there is any deviation from this arrangement, okay, any deviation from this arrangement and particular point, then it's called point defect. Again, the same. In line defect, there will be difference in arrangement of the whole line, this whole line, then it is called line defect. Means deviation from ideal arrangement in the entire row of the lattice point. The whole thing will be deviated, right? So then there is a defect arises. Now again, point defect are further classified into three. One is intrinsic or stoichiometric defect, that is stoichiometric or intrinsic defect. One more would be impurity defect. One more would be non-stoichiometric defect. Non-stoichiometric defect. Right. Done? Yes. So what does it do? What actually happens in stoichiometric? Right. Just see this carefully, understand. Stoichio means balanced. Right. So because of this defect, intrinsic, what you should remember, there is no disturbance in stoichiometry or solid. So no disturbance, nothing will happen. Means there's no disturbance. Though there is defect, no disturbance will happen. Now here in impurity defect, what happens when this arises? When there is a foreign atom, means a different atom is present in the lattice site. right? Suppose if it is NaCl, then you have strontium chloride, cadmium chloride, AgCl, like that. So if certain impurities are present in the crystal, then this defect arises. That non-stoichiometric defect, it disturbs the stoichiometry. It will disturb the balance of the whole solid. Remember that, right? Once again, stoichiometry means does not disturb the balance of the solid. Impurity means it arises due to presence of certain impurities, like what are they? So, okay, what are they? It will be like strontium chloride, it can be cadmium chloride, it can be AgCl in NaCl crystal. So non-stoichiometry, it will disturb the what do you say, stoichiometry, or it will disturb the arrangement of or the balance of atoms in the solids. That further, stoichiometry is again divided into, let us see one more classification. Stoichiometry, if I have to take further, as I said, it does not change the or it does not change the balance of the whole solids. Stoichiometric defect is again classified into the first one, vacancy defect, and the second one is interstitial defect. Interstitial, TITIAL, interstitial defect. Third would be Frenkel defect. Fourth would be Schottky defect. Schottky, TTKY, right? So vacancy, nothing. It's basically how should I remember in the exam? Vacancy means lattice sites vacant. That means suppose if there is a lattice site, one cation, anion, cation. So here cation, anion, cation, anion, cation, anion. Here anion, cation, anion. So if site one of this one cation is missing, so what will happen? Automatically there is a defect. That means if vacancy defect means if one of the lattice site becomes vacant, then it is called vacancy defect. One of the lattice site are vacant. So what is the consequence of this? Density of the crystal decreases. Remember, this is where they'll ask you interstitial defect. Now suppose interstitial defect, it arises when the constituent particles occupy the interstitial site. That means suppose cation, anion, cation, anion, cation, anion. Now anion, cation, like this, right? Again below the anion you have cation. Below this, one of the anion, it occupies the interstitial site. Just see here, I am taking this interstitial defect from here. One will occupy the site like this. So again smaller, bigger, smaller, bigger, bigger, smaller. So it will go and occupy an interstitial site. See here, let me mark it with sketch pen. It will go and occupy this site. I am talking about this site, right? So if it occupies interstitial site from its origin point, then it is called interstitial. Here what will happen? Because of this, density increases. This is important. Now when it comes to Frenkel defect, what should you remember? Frenkel, remember nothing, students. Frenkel means compulsory smaller atom, that is smaller cation. Frenkel means your keyword should be smaller cation. So what will happen? Smaller cation, it dislocates, it will move off from the lattice sites. Okay, so if I have to draw cation, anion, cation, anion, cation, anion. Now for this small cation you have anion, for big anion I have cation, correct? Again bigger, smaller, bigger, right? Smaller, bigger, right, students? So here cation is it. This cation, it will move off. Now suppose if I take this cation, will come and occupy the interstitial space here. It will occupy the interstitial space. Means there is one more here, but it will also occupy the interstitial space. One more, it will come and occupy the interstitial space. From here it will occupy the interstitial space. Or suppose if I take from here, it may go and occupy here. Let us take out this, it's confusing. It may occupy here. Suppose if the cation moves away, means if cation, smaller cation dislocates, what will happen to the density? no change in density. Okay, no, they'll ask you no change in density. They'll ask you which is the defect where there is no change in density. Frankel, you have to say, right? Right, simple. It has moved just to the lattice site. Now, Schottky. In Schottky, what will happen here when lattice sites are vacant? One of the lattice sites is vacant. Suppose cation, anion, cation, anion, cation, anion, anion, cation. Right, right. Again, smaller, bigger, smaller. Now here the vacancy. See here, cation, and okay, this should be here, isn't it? This is okay. Let me join this. Next line I'll put cation. It should be anion. Now this should be cation, isn't it? Here it is missing, and again anion, cation, anion. See here, what happened here? There is vacancy in the lattice site. Correct, because of the vacancy in the lattice site. Yes, students. So what will happen? The density of that. Okay, it can be vacancy, arises vacancy in the lattice sites like Schottky. So basically, we said Frankel is due to the cation. Correct. This type of defect is found in ionic compounds. You need to remember that in Schottky. So here, this is due to equal number of cations and anions missing. Both the sides. Here only cation was missing. In Schottky, equal number of cations and anions both will be missing, right? So now which is missed out? Cation is missed out. Now at the same time, next row I'll draw. So smaller, now here bigger, smaller. This one I'll skip out, and then I'll draw a bigger one. So small. Okay, this should be a smaller one. So here what should happen? Here one. So here which one? Here anion is missed out. Here which one? Cation is missed out. So equal number of cation and anion if they missed out, then it is called Schottky defect. What will happen because of this? Because of this, density decreases. Density decreases. So remember, students, here vacancy, density decreases. Interstitial, density increases. Frankel, no change in density, and Schottky, density decreases. So they will ask you which is a defect where there is no change in density. You need to say it is nothing but Frankel defect. Right. So in today's video, let us come back and finish the last topic of your solid state chapter, that is properties of solids. Right. So in properties of solids, basically in grade 10th, we have studied the arrangement of atoms. Solids are tightly packed, liquids, there are gaps in between, gaseous state because of the property of diffusion, the lot of spaces. Those are quite common. But here, when you go to your grade 11, 12, you need to know the two important properties of solids. That is, electrical properties is one, electrical properties, and one more property is magnetic property, right? Magnetic. So basically, when I have to speak about electrical property, so we are going to study about depending upon the conducting power. So solids are divided into three varieties. Following means basically four. I have to say four varieties. Right? What are they? As I told you, conductance or conductivity is the main factor which we are taking into consideration, right? So based on the conductivity, they're classified first into electrical, are classified into conductors. They're classified into semiconductors. They're classified into insulators, and a property which I'm going to teach you is nothing but superconductivity. I'll say that also. When I have to speak about the magnetic property, okay, let me draw one line like this, right? So when I speak about magnetic property, types of magnetic property, the different types of magnetic property which I need to study. What is the first one? The first one is diamagnetic in nature. Diamagnetic. We will see how the domains are reached. The next variety is paramagnetic. Next variety is ferromagnetic. Next variety is antiferromagnetic. Next would be ferrimagnetic. Ferrimagnetic. Right? These are the different types of magnetic properties. Now, when I have to speak about the conductors. So basically in conductors, as we know, they conduct the movement of electrons, or the conductivity or conductors. The solids, the conductivity is very high, means due to presence of electrons, isn't it? So because of the presence of electrons, the conductivity is too high. And how much is the range? It's basically 10 to the power of 7 units are ohm meter inverse. Where is it found? Basically examples are metals. Yeah. So when I speak about semiconductors, what is the conductivity range? 10 to the power of minus 6 to 10 to the power of 4 ohm meter inverse, right? Done. When I speak about insulators, where there is no flow, means in insulators, what will happen? The conductivity range is very high because of the almost absence of the flow of electrons. How much is it? 10 to the power of minus 20 to 10 to the power of minus 10. So what is the unit? Ohm meter inverse. Done. So here semiconductors, when I have to speak example, semi-metals I can take example. When I take insulators, examples are non-metals. Students, non-metals. So this is important for you. They may ask you 1 mark question in this, right? How do they ask? What is the conductivity range of conductors? Why is it showing high conductivity? We can write because of the presence of valence electrons or the free electrons, which will move through the bands, isn't it? Yes, in conductor there is no gap, isn't it, between valence band and conduction band. But in semiconductors, there is a gap between valence and conduction band. Correct? Means the gap is very between this one is small. So what will happen to the conductivity? Conductivity is low. But again, in that this one we have studied about N-type and P-type semiconductors. So N-type means it's nothing but group 14 elements doped with 15. P-type means group 14 when doped with group 13. They form P-type. That is a semiconductor. And insulators, we very know the energy gap between both the bands is like large. That's why the electron can't jump. That's the reason the conductivity is so much, right? Now let's come back and see the magnetic property of solids. Now let us come back and see the types of magnetic properties. What did we say? What are the different types? Diamagnetic, paramagnetic, ferromagnetic, antiferromagnetic, and ferrimagnetic. Now what is the difference between those? We'll see. So when I have to take the first one, diamagnetic. Now let us see the domains, how are the magnetic dipole moments, or how are the electrons arranged in this. So alignment of magnetic dipole. So when I have to see in diamagnetic substance, one is arranged like this. All the electrons are paired. See here, this is electron, first pair. Now next one, next pair, one more pair, isn't it? So because of this pairing, when they are paired like this, what is the advantage of this? They are feebly repelled by the magnetic fields, because completely, isn't it? Because due to the existence of paired electrons. So you have to write which are feebly repelled. What is the example for this? If I have to say TiO2 example, vanadium pentoxide, one more example, sodium chloride is one more example, right? Where are we using diamagnetic substances? In insulators. That. So when I have to speak about, because of this pairing, they are feebly repelled in the magnetic field. When I have to take the paramagnetic, just see how are the electrons or how are the dipoles arranged. It's like this, up, down. Next, see this arrangement. The arrangement is not proper, isn't it? When I see diamagnetic, it is perfectly paired. That's why they feebly repelled. But here, all the electrons, means only one, at least one unpaired electron will be there. Like this. Here all are paired. Here at least one unpaired will be there in paramagnetic. Done, students? So what will happen? They are attracted by the magnetic field. Yes, why? Because of the presence of unpaired electrons. So feebly repelled by magnetic field. Here attracted by magnetic field. I am writing MF. What is the example for this? Basically oxygen, copper, TiO, Fe plus 3. All these are examples. Where am I using? I am using in electrical appliances because of this unpaired electrons. Done. So next one I have, next category is ferromagnetic substance. Ferromagnetic ferromagnetic substance. So in ferromagnetic, how are the all the electrons are unpaired. Just see students, all are unpaired. Now what will happen because of this? It acts as permanent magnet because all are unpaired, isn't it? Perfectly. Here when they are attracted, because then it is repelled. Here one only, that's why they are attracted. Here all are unpaired electrons. That's why it acts as permanent magnet. Ferromagnetic substance, permanent magnet. What are the examples for this? Iron is one example. Fe, cobalt, nickel. These are the examples. Where am I using this? Basically, if I have to take CrO2, I'm using it in videotapes, isn't it? Right. So, when I have to take the next one, that is antiferromagnetic. So in antiferromagnetic, how is the alignment? Just see, up, down, up, down, up, down. Here, net dipole moment becomes 0. So everything is balanced, isn't it? So net dipole moment is 0. So where are we observing this? In which one? Examples are, if I have to give you MNO, FeO, Fe2O3, done students. So when I have to take ferromagnetic, the last type of last magnetic property, that is here, how is alignment? Up, down. Now observe, how many unpaired electrons? 3. So this arises when there is a net dipole moment, isn't it? Yes, ferromagnetic net, because here the alignment is 1 up, 1 paired, again unpaired electrons. When there is a net dipole moment, ferromagnetic is observed. So arises when there is net dipole. Right, students? Yes. Okay. Right. So what is an example of ferromagnetic which you can remember for the exam? Yes, you can write. Best example is Fe3O4. Right. So best ferromagnetic example is that. So this is your magnetic property, different types of magnetic property. All you need to remember is the domains, and you need to remember what will happen there, and the examples. What will happen to the dipole, whether it is attracted, which is repelled. They may ask you, what is the type of magnetic property when it is feebly repelled, and why? Then you need to explain, because of the paired electrons, it is diamagnetic, and these are the examples. Right. Thank you for watching, students.